Hazard Identification and Risk Assessment, or HIRA, is the operational core of modern workplace safety. Many organizations treat a risk assessment form as the final goal of safety management, viewing the paperwork as the objective rather than the starting point. A risk assessment conducted in isolation fails to provide protection. Without a surrounding structure to enforce its findings, the document has no utility. To function, a risk assessment must exist within an active occupational health, safety, and environment management system. This system provides the assessment with a constant feed of monitoring data, incident reports, and review cycles to keep the safety protocols accurate. To build this process, we need to map how it functions. We will define what risk actually is, trace the explicit steps of the HIRA process, and demonstrate how to quantify consequence. Establishing a foundation for safety requires a precise lexical understanding of risk itself. Hazard identification operates as the sensory nervous system of an organization, tracking operational threats so the broader management system can neutralize them. The foundational safety axiom is straightforward. You cannot control a risk without accurately defining the hazard. In occupational health and safety, a hazard refers to the source of potential harm or exposure. It is the physical condition, substance, or object. Risk describes the consequence, the specific combination of how likely the harm is to occur and the severity of the resulting injury. If a bottle of chemical solvent spills on a hospital floor, the pooled liquid represents the hazard. The risk involves the likelihood of a nurse slipping and the severity of their impact against the floor. Environmental standards employ different terms for this same conceptual relationship. Instead of a hazard, environmental guidelines define an aspect. This is the source of an organization's interaction with the natural world. The resulting consequence, the physical change to the environment, is classified as the impact. A leaking diesel pipe at a storage facility is the aspect. The soil contamination spreading toward the groundwater is the impact. Identifying the source of harm is a starting point, but mapping the specific consequence yields the data required to prioritize organizational resources. This flowchart displays the formal HIRA process flow, which serves as the engine for mapping those consequences. Step 1 requires establishing a plan to determine the scope of the assessment. Step 2 focuses on physical hazard identification, where safety teams locate specific danger points within the operation. This graphic illustrates a standard construction environment. Identifying hazards means logging open shafts, unsafe scaffolds, and unguarded machinery operating in this space. Once the sources of harm are logged, the process advances to steps 3 and 4, analyzing and evaluating the risks attached to those identified hazards. This grid shows the primary tool used for evaluation, the 5x5 prioritization matrix. The matrix quantifies risk by multiplying the likelihood of an adverse event occurring by the severity of its consequence. Consider a busy forklift route that directly intersects a blind corner on a pedestrian walkway in a distribution warehouse. The probability of a collision is high, and the consequence is a potential fatality. This calculation produces a red high-priority score that demands immediate intervention. The matrix replaces human subjectivity with an objective data point that leadership can confidently act upon. That data point triggers the 5th step of the HIRA process, risk control. Every hazard carries an inherent level of danger known as raw risk. This is the total threat present before any safety interventions are implemented. Working at the bottom of a newly excavated, unsupported construction trench carries an extreme raw risk of fatal crush injuries. This chart displays the hierarchy of controls, the methodology used to reduce that raw risk. The bottom tiers, administrative controls like warning signs and personal protective equipment, represent the weakest lines of defense. A plastic hard hat cannot protect a worker from thousands of pounds of collapsing soil. Relying solely on PPE leaves the raw risk high. Moving up the hierarchy to engineering controls provides a more effective solution. By installing heavy steel shoring to brace the trench walls, we physically alter the environment to isolate the worker from the hazard. With those steel plates in place, the remaining level of danger is the residual risk. This is the threat left over after effective controls have been implemented. Identifying the gap between the raw risk and an acceptable residual risk and engineering the controls to bridge it is the operational purpose of HIRA. The vacuum problem is now solved. We have the components required for a functional safety system. These steps function as a cyclical engine within the management system. First, HERA is an active cycle. Second, hazards are sources of harm, risks are consequences. Third, aspects create impacts. Fourth, prioritize threats objectively. Fifth, controls bridge raw risk to a safe residual level. You now have the structural blueprint. The challenge shifts to applying this framework on a complex, moving operational floor. Safety requires continuous control of consequential risks. Next time, we test this framework in practical assessments.